Howdy folks. So in this section we're going to learn various substitution techniques, and the idea of a substitution technique is essentially to take a differential equation that we don't have a current tool to solve and perform a substitution so that it looks like something that we do know how to solve. So for example, we already saw this with our Bernoulli substitutions, where we did a Bernoulli substitution on an ODE and we got down to something that we could solve using the integrating factor technique. So what we're going to do here is we're going to look at sort of a smorgasbord of various substitution techniques. And in my opinion, the easiest substitution to do is called the linear substitution. And it applies if our right-hand side of an ODE in normal form looks like f of ax plus by plus c. And the key idea here, and so notice that a could be 0, b could be 0, c could be 0, or they could be any values. But the key idea here is that we only have a function doing something to a linear expression here. And if that's the case, we're going to use the substitution u is equal to ax plus by equals c. Okay. So I'm going to let you guys actually do this problem. I'm not going to show you how to do this problem other than to set up the substitution. But let's just talk about this for a minute. Here I've got a differential equation. It is first order, but it's not linear. Why is it not linear? It's not linear because of this squared term, and if I were to FOIL that out, that would give me a 3y, or that would give me a 9y squared at some point. And it's that squared component that makes this nonlinear. So this is nonlinear. So it's not linear. It's not exact, and you could put it into differential form if you wanted to, but it really isn't exact. But it is of this form where we can think of the right-hand side here as, even though the function is the squared function, right? Capital F here, in this case, capital F of x would just be the function x squared. It's the squared function, but we're inputting in some linear expression of x, y, and constant. And so if that's the case, we can do this substitution that I'm talking about. So our technique here is to go ahead and let u equal x plus 3y plus 2. Then as a consequence of that, if I were to differentiate both sides with respect to x, just like how you do a u substitution in Calc 1, differentiate both sides with respect to x, in this case gives me du dx is equal to 1 plus 3 dy dx, and I'll write plus 0 there. So I implicitly differentiated that right-hand side. Okay. Notice that this is going to be very easy to solve for dy dx. And the key reason why this is easy to solve for dy dx is that that's just a number because x is linear. And this doesn't have a y component in it because it was also linear. When we differentiated it, we don't have any y component, meaning it is straightforward to solve for dy dx. And if I were to do so, if I were to solve this for dy dx, what I end up with is, let's see here, 3 dy dx is equal to du dx minus 1, or that dy dx, in this case, is equal to 1/3 du dx minus 1/3. So what I'm going to do now is I'm going to go ahead and substitute. Let's go ahead and number these. Let's call this one and this statement, let's see, box that. We'll call that statement 1. We'll call this statement 2. And let's substitute this into the original ODE. So if I do that, what I'm left with is, in place of dy dx, I'll write 1/3 du dx minus 1/3 is equal to the right-hand side, but we've replaced that linear expression with u, so I just get u squared. I can clean this up pretty easily by multiplying both sides by 3, so I get du dx minus 1 is equal to 3u squared. And now I've got a much simpler differential equation here that I can solve. So in fact, while this new differential equation is also nonlinear, it is now separable. And so I can use the technique of separation of variables on this new ODE. So I'd like you to go ahead and solve this. When you're done, you'll have a function in terms of u And then what you'll need to do is, just like you did in an ordinary U substitution in Calc 1, is you'll have to do a back substitution. So now U finish. And if you like, I've included a solution for you, but please, you need to try this on your own and then give it a shot and then just check your work. Thanks, folks. We'll see you in the next video.